Function inverses. F to the negative 1 of x is the notation used to symbolize the inverse of the function f of x. An inverse reverses the action of a function. F of x and g of x are inverses if f of g of x equals x and g of f of x equals x. They both need to be checked. In other words, their composite brings us back to where we started, back to x. For example, let f of x equal 2x plus 3 and g of x equal x minus 3 all over 2. Let's check if f of x and g of x are inverses. So first, let's find f of g of x. Here, the main function is f of x, and g of x will be used to replace all the x's in f of x. So we get 2 times something, which is x minus 3 over 2, plus 3. If we distribute the 2 to what's in parentheses, we are left with x minus 3, and we still have plus 3. The minus 3 and plus 3 cancel out, and we get x. So we're halfway there. We've shown that f of g of x equals x. Now we need to check g of f of x. Here the main function is g of x, and we're substituting in f of x for x. So we will get something minus 3 all over 2, and we'll put 2x plus 3 in for that something. So we have 2x plus 3 minus 3 over 2. Here we'll simplify the numerator first, and the plus 3 and minus 3 cancel out. We get 2x over 2. Here we can cancel out the 2's, and this simplifies to x. So both f of g of x and g of f of x equal x. Therefore, yes, f of x and g of x are inverse functions. Okay, we have something called the horizontal line test, not to be confused with the vertical line test. Here, if a horizontal line crosses the graph of a function more than once, the function does not have an inverse function. It may have an inverse relation, but not an inverse function. For example, if we look at the graph of this parabola, drawing a horizontal line here crosses the function in 2 places. So that means its inverse is not a function. It has an inverse relation, but not an inverse function. The graphs of inverse functions have an interesting property. Or you can find the graph of an inverse function by reflecting the graph of the original function over the line y equals x. For example, here we see a graph with f of x, f to the negative 1 of x, and the line y equals x. So here's the original function, y equals f of x. If we graph the line y equals x and reflect our original function over that line, we get the blue function, which is the inverse function. Similarly, with this parabola, our original function, f of x, is our parabola. If we have the line y equals x and reflect our original parabola over that line, we get this blue function and this, blue relation. And as you can see, this inverse does not pass the vertical line test. It's not a function. And we could have predicted that by looking at the original function, the parabola, using the horizontal line test and seeing that a horizontal line passes through more than one point. So that predicted that our inverse would not be a function. Also, and this will be helpful when you're graphing inverses, if x comma y is a point on f of x, then y comma x is a point on the inverse function of x. So the points switch the x and y values. For example, if 2 comma 5 is a point on f of x, then if we switch the values, 5 comma 2 is a point on the inverse function of x. Let's find inverses algebraically. For example, f of x equals 5x minus 2. To find its inverse, first, replace f of x with y. So we simply get y equals 5x minus 2. If our original equation doesn't have an f of x and starts with y, we would skip this step. The next step, swap x and y. So where y is, we'll put x, and where x is, we'll put y. That gives us x equals 5y minus 2. If there were exponents involved, the exponents would stay where they were. They would not follow their original variable. Next, solve for y, or get y by itself. So first we'll add 2 to both sides and get x plus 2 equals 5y. Then we'll divide both sides by 5, and we'll get y equals x plus 2 all over 5. You can reverse this so that it actually reads from left to right. Y equals x plus 2 all over 5. And then finally, replace y with f to the negative 1 of x. So our inverse function of f of x is x plus 2 all over 5. Let's check that. So let's check, remember from the previous slide that f of x was 5x minus 2. We found its inverse to be x plus 2 over 5. And let's check their compositions. So f of f to the negative 1 of x, we'll start with the f function, so 5 times something minus 2, and substitute in x plus 2 over 5 for the something. So 5 times x plus 2 over 5, the 5's cancel, we're left with x plus 2 minus 2. Here the plus 2 and minus 2 cancel out, and we're left with x. And let's check f to the negative 1 of x of f of x. Here the main function is the inverse function of x, so something plus 2 over 5. That something will be 5x minus 2. So we have 5x minus 2 plus 2 over 5. We simplify the numerator, the minus 2 and plus 2 cancel out. We get 5x over 5. The 5's will cancel out, and we get x. So, yes, we've just verified that f of x and f to the negative 1 of x are inverses, or that we found our inverse correctly. So try this. Find the inverse of f of x equals 3x minus 1 over 4. Pause this while you try this, and then check your answer back here. Okay, so our original function was f of x equals 3x minus 1 over 4. Replace f of x with y. We get y equals 3x minus 1 all over 4. Swap x and y. That gives us x equals 3y minus 1 all over 4. Now we need to get y by itself. So start by multiplying both sides by 4. We get 4x equals 3y minus 1. Add 1 to both sides. That gives us 4x plus 1 equals 3y. And then divide both sides by 3. So 4x plus 1 all over 3 equals y. Or f to the negative 1 of x equals 4x plus 1 all over 3.